has a gain, it has an output resistance, or in or out. Then you put it in series with your signal source. And this is AV naught, right? That's R6. And this V out over V6. What was it? Open load. V out over V6.
R out divided by R sig relevant R.
AV naught V out over VI, right? V out over VI. Now I'm looking for V out over V6.
What is VI?
Yeah, it's voltage divider. So
V sig is hey, is that a volt?
Voltage divider?
Or is that a current source?
The voltage source. So the other one is V6.
No, the dependent one.
That's a voltage source.
Oh,
That's R. Above that is R O.
That's a voltage source that isn't V out, just AV or VI.
yeah, okay.
Oh, okay, I got you.
So you just multiply that by VI divided by V6, right?
So V out over V6, I'm sorry, is equal to V out over VI times VI over V6.
Mm-hmm.
And V out over VI is AV naught, VI over V6 is,
We cancel out, yeah.
It's the voltage divider. Okay.
I see, yeah.
and
Nice.
that's it. So we're doing the same here too, right? So this is actually why we said R in has to be infinity, right? Because this
Oh, the
goes
guys
to
are here.
1 when R in is infinity. Right?
Right.
Yeah.
So I'm doing the same thing, it's just now you have an amplifier, and there's an R in here. So V out over VI is minus GM, whatever resistance that you see there, which is RD in parallel with RL in parallel with R naught. And then that multiplied by R in divided by R in plus R sig is V out over V sig, which is the overall gain, right? It's the
Yeah.
same thing. Actually, that's why we want to calculate R in and R out and the gain for any amplifier, so that we quickly put it back to this model, and then we can calculate gain for any situation. Okay? And then the complete gain, when you connect it to a load, what is that?
Another one.
In this case, what is V out over V sig this time?
Same thing.
V out over VI is V out over VI, or negative.
It's two voltage
V out
dividers.
over VI times VL.
Is RL?
Or R out.
Give me an equation.
Negative.
The current is negative.
There's no negative.
So it's negative AVO. That's,
Why is it negative?
Because the current's flowing backwards through the output resistor.
isn't it?
Who said that?
So it's just AVO, I
I can't
guess.
see the arrow.
Yeah, is that
There's
just
no arrow.
that's just a G in the diamond, and then above that's R O U.
I was just assuming that in the
Or
diamond,
out.
the current was pointing down.
That is the voltage source. That's what we were asking earlier.
Would it just be AVO times RL over RL plus RL times
Yeah.
RN over RN plus RC?
Oh,
Yeah, alright.
RC. Yeah.
right?
Yeah.
Nick? intuitive by now. If it's not, make sure that it becomes intuitive. Go home, write KCL and Ohm law, and make sure that this is intuitive, because this actually we calculated back in the day, right? First few weeks of the class, writing KCL and Ohm law. It's just simply writing KCL and Ohm law. That's all you need to do. But after that, when you wrote it once, twice, third time, this has to become intuitive to you. Yes.
I mean, here's the thing, the V-Sig has an I in it, which makes it seem like a current source, and then, like, I thought that thing was a current source over there, so that's the thing that was.
If it's a current source, I'm not gonna call it V-Sig.
Right, but I'm
Call
just
it
saying,
I-Sig.
I'm just saying, whenever I was looking at that, I was like, okay, so it has current source over there, current source over there, I was just, trying to derive everything based on that. I mean, obviously, if it's a voltage source, it's gonna be voltage divider, yes, I see that.
Okay, so there are few things that I have to draw things more visible, I assume, but there are things that I assume you know by now, and that actually helps, that I don't write visible, and then you have to make sense of things using your knowledge. First of all, if it's a current source, like I said, I'm gonna call it I-sig. But on top of that, if it's a current source, I'm not gonna put it in series with an R-sig. It's gonna be in parallel with an R-sig.
Right.
Same in the output. If you have a current source, you're not gonna put it in series with a resistor.
With
It
R
comes
out,
with
it's gonna be-
it's gonna be in parallel with R out. So knowing all that side
Norton's,
information,
right,
you have to
Norton's
judge
theory.
this and know that this is a
Norton.
voltage and
Oh,
that's a
Norton,
voltage.
yes.
And it's
Jason.
good that you don't know it, now you know it.
Yes.
Okay, when you see this, you cannot get
Okay,
confused knowing that a voltage source is series with an internal resistance, a current source is in parallel with an internal resistance. Okay? So basically, if I get these three components off of my amplifier, say this amplifier, then I can put it back into that three component model and then connect it to the source and connect it to RL and just calculate the gain based off of that equation that I showed, right? So you may think that, well, calculating this with RL here, it looks kind of different because RL is part of the gain. Well, yeah, I mean, we included RL in the gain, but that's fine. You can actually calculate R out and then remodel your amplifier using the three component model and then connect it to RL and R-sig and use that equation to calculate the gain, and you're gonna get the same equation. Like this, minus GM R, and actually this is pretty easy to see. RD in parallel with R naught
RL.
times
Oh.
RL over RL plus RD in parallel with R naught is the same as these three in parallel to each other.
Yep.
You write it down. RD in parallel with R naught times RL divided by RL plus RD in parallel with R naught is equal to RD in parallel with R naught in parallel to RL. Interesting, right? And this is your R out. That's your R out. So I'm using R out times RL. R out plus R out. So this part you see, that actually is the equation that came out here. Okay? So do it at home and you're gonna see that they become the same. So either way that you do it, you're gonna see the same result. So now let's move on and talk about other types of amplifiers. So this is a complete common, what? Terrible?
Common
It's a common gate amplifier. Why is that?
Because
The gate does not have anything to do with the input or output.
The gate is connected to ground.
That's not why.
It's because it doesn't have an input.
You got the output on the drain and the input on the source.
Yes, because the input and output are connected to source and drain, and gate is not connected to neither. Austin, if you go by which one is connected to ground, you're gonna get confused as soon as I don't connect anyone to ground.
Okay.
Okay? You go by input and output.
Okay.
So it's a common gate, yes.
Can you say why it's a common gate one more time?
Input is connected to the source, and output is from the drain.
Did I tell you it already?
And gate is just common between the two. We're not connected to any of them. Yes.
So cool.
No. No.
So on PMOS, the
Same.
is still on the source.
In a PMOS, this is gonna be positive power supply, this goes in, and that's gonna be the negative power supply. Okay? You still connect to the source and take your output from the drain. But everything is flipped. It's gonna be positive, current goes in, and that's gonna become negative, but everything else will stay the same.
There was more than one transistor. Common gate, drain, source, like you mentioned, there's more transistors.
If there are more transistors, in which way?
Like one transistor controlling, I guess, the gate of that transistor.
You mean like cascading amplifiers?
Yes.
Yeah, you're not gonna be asked those kind of questions, but yeah, I mean, you go from, again, if I connect this to another amplifier, so there's gonna be the input of that amplifier and the output from that one. So output of this one is input of the next stage. And then you judge the next stage based on the input and output of that specific stage. Okay?
So the conventional is the same.
But we're gonna only focus on single stage amplifiers in this class. There's no cascade. Okay, so why do we have these capacitors here? These two?
Decoupling capacitors.
Decouple them.
Decoupling capacitor.
Decoupling.
They are decoupling capacitors. What do they do, Jason?
When you bias it and you look at the large signal analysis, it separates it out where you can get your values for the small signal AC.
Exactly, because if I don't have that, then the current of that circuit is no longer I. Right? I mean, it's just gonna come here in a split. You don't know what the current is gonna become with something else. But I wanted the current for this circuit to be I. So I actually put a capacitor there so that when you connect this, it's just separated. DC current doesn't change. The output is the same. You don't want the output to be something while the input is zero, right? Because if this input is zero and if you don't put a capacitor there, you still have a voltage in the output. You don't want that. You want zero in the output when the input is zero, right? And also, you don't want the value of that to change based on the DC value of that to change based on the value of RL. So you're decoupling DC from AC. Yes.
I think one thing that's confusing me about this diagram is why is that current source 0 on there, and I guess the current directions.
Why is the current source 0? You mean this?
Yeah.
That's only for AC.
It's only for AC.
For
Okay.
AC analysis. When you do AC, it's open, right? So that turns into this.
Okay.
Okay. That's only AC analysis. Because when you do AC, anything DC is gone. When you're doing AC analysis, you're only dealing with change. Changing the voltage, changing the current. So
Okay.
everything that doesn't change is gone. Like this current source, it's not changing, right? So it's gone. The power
So-
supply voltage, it's
so
not
I'm
changing,
assuming-
right? It's gone.
I'm assuming in AC, that dependent current source in the second diagram is negative.
Dependent current source, which one? This?
Yeah.
It's negative? What do you mean by negative?
I mean, the current is most likely flowing up.
Doesn't matter.
Okay.
It's just a function of VGS, right?
Right.
So it's GMV, that is GMVGS. whatever. If VGS is negative, then that's negative. If
Okay.
VGS is positive, that's positive. Could VGS be negative?
And PMOS.
Yeah,
No, this is
not,
an NMOS.
It
Oh,
just makes,
no. No.
it turns
It wouldn't
into
turn
a
it on.
PMOS, doesn't it?
If
It wouldn't turn it on.
Signal, then it would just make the
Half
signal
on.
flip upside down and just shift pretty much.
But the source flows in on a,
Like
See,
being
if I
hot.
put a positive voltage here, this gate source voltage is gonna get negative.
If it gets negative, then it'll just open up the channel and it won't let anything through. Like, you will effectively.
That's my question. So it doesn't work the way that we have it,
Yeah,
right?
no good.
I say it goes the opposite direction. You applied,
Opposite what direction? Well, with that model, yes. I mean, if you put negative voltage, then the current is just gonna go the other direction.
Yeah.
Right. But can you put a negative VGS on the device?
You could.
No, you're
It's not gonna be in saturation.
It's not,
Yeah. Biased by that negative
Yeah.
VSS, so if the signal's negative, it's still gonna interfere.
You're gonna unbias the transistor, nothing will fall through.
It's not gonna work.
I'm not sure if I understand what you're saying, but I suspect that you're correct.
Can we just go with that? I don't wanna talk about it.
I don't see.
oh, wait. Okay, so in a PMOS, you have PN, right? That's it, or I'm going backwards, it's NPN in a PMOS?
PMOS?
PMOS,
NPN
yeah.
and PNP is for BJT.
For BJT? So, I mean, you're saying you basically apply, VGS is opposite, so VGS is opposite direction, right?
That's the thing, it's not. I want you to realize that.
Hey, I have an easy
The
way.
voltage being negative in that model, that doesn't mean VGS is negative. Now tell me why.
It's just-
If the voltage,
You're not
if
gonna
this
overcome-
VGS is negative, doesn't mean that VGS here is negative.
Oh, that's because we have a negative, voltage source on the bottom, and in that model, we're just making that an open because of the convention of, AC analysis.
You're now saying the same thing as Locust did.
I didn't know
I didn't hear it.
He said that it bias, the bias changes. Isn't that what you said?
The bias.
I'm just saying that if you apply negative VGS.
There's a
to that
VGS
circuit,
here,
it's not-
right? VGS is something.
Right.
Whatever that is. It's, in this circuit, there's a VGS. It's saying, based on it, this current, you're gonna get a VGS. And that VGS is positive. And let's say just, for the sake of discussion, this is 2 volts. VGS is 2 volts, okay?
VG.
What's VGS in that circuit?
2 volts.
If I don't have any signal.
You don't have any signal?
2 volts.
No.
Well,
It's
zero. Zero.
Because the VGS, the DC voltage was
Reflects.
constant, I ignored it. That's why you don't see it over there. So if I put a negative 0.1 volt here, this VGS is gonna become 1.9, not negative 0.1. See, this is all about change. So when I say a small GS is negative 0.1, that's change of VGS, not the actual VGS. The actual VGS is 2 minus 0.1, is 1.9. Okay? So that VGS, that becoming negative, doesn't mean that this is becoming negative. This is becoming smaller. That becoming positive, that means that this is becoming larger. Anything positive adds to the DC values here. Anything negative subtracts from the DC values here. Someone had a question, Jeff?
Okay, you said on that right picture,
Uh-huh.
VGS would be 0?
Yeah, if this is gone, I mean, if I don't have any signal.
Yeah, okay, yeah, I can see that.
Is that whole change thing because of that capacitor right there? The C1?
CC1. Yeah.
Yeah, CC1.
What do you mean? If I remove it,
I mean, like, yeah, if you remove
I
it.
can't remove it. If I
Okay.
remove it, it's just whole thing is not gonna work.
Messed up.
Okay. So the capacitor there, that's the reason why the VGS is a cumulative change, not.
No,
and
that has nothing to do with the capacity.
Okay.
It's just the fact that in our analysis, we ignore the DC voltages and currents when we do AC analysis.
Okay.
So there's part of this circuit that you don't see in that circuit. That's what I'm saying. So that's why I'm saying with the AC model, you're only dealing with the change in the voltage, change in the current, not the actual values. Okay, what's the gain in that circuit?
Yeah, it's negative.
Oh, you have to first ask if not
RD
negative.
parallel RL.
You have to
plus
first
G.
ask which gain. So we have V out over VI, and we have VI over V6. So what's V out over VI?
Is that RD?
Or
Parallel RD
Don't guess.
plus 1 over G divided by G.
If you're not doing it right now, you're not going to be able to do it in the exam. I guarantee it.
Take a piece of paper.
Yeah. All three are wrong, Andrew.
easy, Andrew. I don't need a real hard test.
Yeah.
So, no, you're an exception right now.
President, yes, that that dependent current source,
Uh-huh.
does that not run, into the ground at the gate?
It is connected to ground, but there's no current gonna go to ground. Just remember, with the team, that's a team model, right? IG is 0. So, this current here is 0. There's no current going in.
Yeah, I got you.
But the value of the voltage is 0. The AC value of the voltage is 0. It's ground. But there's no current going into that. So gain, Jason,
Yo, it's VD, RL, and parallel with RD.
again you have a voltage in your equation for
It's
the
not-
gain.
no.
I'm fixing to cancel it out as
Okay.
I
RD in parallel with RL,
Yep.
and then what?
Okay, and, well, okay, do we include 1 over GM right there in finding VI? It's part of the actual amplifier, but when we say that it is.
That you're not asking the right question. What do you do to calculate the gain?
You find VI and find the in.
No, what do you do? What? Focus?
KCO and Ohm's law.
Exactly. Have you written KCO and Ohm law?
Kind of like a modified version.
There are 2 Ohm laws here,
Wait, I'm
and
gonna
that's
be
it, I
laughing
can
with this
do gain.
idiot.
Are we doing V out over V sig or V out over V?
V out over VI. Doesn't matter, right? Like, see, for V out over VI, there are 2 Ohm laws. For V out over V6, there are 3 Ohm laws. So locus, what is the gain?
I'm not there yet.
For RD in parallel with RL, I call it R out. 0 minus V out divided by R out is I. And then for 1 over GM, 0 minus VI divided by 1 over GM is I.
You said that last one again?
0 minus VI divided by 1 over GM is I. Just equate the two equations.
Yeah, I got you.
And you get GM RD in parallel with RL. With GM R out, right?
Yep.
So the gain is very similar to what you had for common
There's a
source.
negative sign
It's
in
just
that
positive.
equation, right?
What?
Is there a negative sign in that equation?
No. The gain is positive for a common gain. The equation is very similar to common source, but it's just positive. What's the input resistance, Max?
Oh man, I haven't gotten that far yet.
1 over
The
GM.
input
It's written on there.
resistance.
1 over GM.
Does it make sense?
Yes.
Why?
Because, VI is between, is VS minus, VG divided by 1 over GM. It makes sense that that's the resistance.
Looking into the source, all you see is 1 over GM between that and ground. So the input resistance is 1 over GM. How about the output resistance? And does that make sense?
I was gonna say actually already in parallel with RL, but I keep forgetting that RL is not part of the.
Okay. Jeff?
You're finding input or output resistance. I guess.
Output resistance.
Well, sorry, the input is what I'm confused on. So when you're finding that, you just ground all your sources.
All you need to do, yes, I mean the process is that you're going to put a current source, a voltage source here, look into the current, and then divide the voltage by the current, and that's your resistance, right? But just let's assume VI is your voltage source for the sake of simplicity. If VI is your voltage source and I is your current, so VI divided by I is 1 over GM. It's simple as that because you only have one resistor there. Between that node and ground, you have one resistor. So what's your input resistance? That resistor. Yes.
What's VI?
What is VI?
It is VC.
No, it's not.
Okay.
What about RC?
So that's the next thing that I was going to ask. And V out over V sig is basically whatever gain that you just calculated times the voltage divider. R in divided by R in plus R sig, right? And R in is 1 over GM. Yes.
Why does RC not matter for the input resistance?
Because
not
you're
part of the
looking
actual-
in to your this is not your amplifier, Jeff. This is not your amplifier. That's not your amplifier. This is not your amplifier. So when I say the input resistance of your amplifier, I'm talking about your amplifier, not your signal source. This is not your amplifier. This is what you designed.
It is 2 more.
And then
It
you
is
sell it to
2.
me.
Yeah.
And then I connect it to a signal source. So before you even sell it to me, you have to calculate the input resistance. So obviously, input resistance can't include parameters that I connect to your amplifier, right? So you're looking into these two terminals, are the two terminals coming out of the box that is called the amplifier. Input, output. So when I say input resistance, you're looking into that terminal and tell me what the resistance is. When I say the output resistance, you look into this terminal and tell me what the resistance is. Which one is zero? For the out is RD. Why is it 0? Because here when you don't have that, and then you're looking in, what do you see? This is gone because when you calculate the input with the resistance, all the voltage sources, the rest of the voltage sources are gone. So that's gone. So VGS is 0. That's gone. You're looking in, you only see RD. Why would you see 0?
I guess I was confused because you had D at one point, and then you have VD at another point. I know it's the same node.
Yeah, they're all the same. VD is the drain voltage and it's the output voltage too. Jason?
You said V out over V in is GM times RD in parallel with RL?
Uh-huh.
Okay.
You're not getting that?
No, not even.
Let's discuss it after the class. So the last type of amplifier that we're going to discuss, and we actually discussed these before, we're just looking at the same amplifiers including the bias circuit, okay? None of this has to be new to you. So again, these two capacitors are the decoupling capacitors. This is your bias, which is now a single current source. The input is to the gate, output is from the source. What kind of amplifier is this?
It is a common drain.
It's a common drain.
Yeah.
Exactly. So the small signal model for the common drain is what you see over there. And the input resistance, looking into this, what input resistance do you see?
RG parallel.
Who said that?
It's just RG here.
No, it's interlinked because you got that capacitor though, right? Like capacitors.
When you calculate the input resistance, you're talking a small signal analysis. For small signal analysis, for AC analysis, the capacitor is a short. You're discussing that circuit when I talk about input resistance, output resistance, or gain. Jeff?
I'm totally confused by what you just said.
By what?
It's all of it, that small signal, all of it. I'm confused as to why, so R in is nothing?
Who said that? I haven't told you what RN is. Did I say it's nothing?
You said that RU is short.
No,
You're
capacitor.
hearing me
Capacitor.
wrong. I said the capacitor is a short. Okay, this capacitor is a short.
Yeah, sure.
Okay?
So on the right side, that's just the AC
Yeah.
models, okay.
So what is the input resistance?
I think it's RG.
Why?
That's all you see before ground.
Applied voltage, AC.
Yeah, you apply voltage, that's what you said.
Right.
IG is 0.
Right. And what's the output resistance?
1 over GM.
Because 1 over GM it's a pretty good approximation if you don't have R0. But since you do have R0, at least in that model, then it's actually 1 over GM in parallel with R0. This is, when you do the output resistance, this is ground, right?
Mhm.
So that voltage is ground,
Ground.
0, since there's no current. So looking back, you have a ground here, you have a ground there. So you see 1 over GM in parallel with R0. If you didn't have R0, it was 1 over GM. And if you do, even if you do have R0, 1 over GM is a pretty good approximation because R0 is much larger than 1 over GM. Yes.
So you're saying that when you calculated that, you based it on the assumption that our VG was ground?
See, this is, you're repeating yourself, Jeff. When I calculated resistance, I always do the same thing. I don't change, right?
Okay.
I put a voltage source and the rest of the voltage sources in the circuit and the DC current source in the circuit, they're all gone when I do that,
but
okay?
IG
So,
is 0.
so this is gone, right? This is gone.
Yeah.
When it's gone, it's a ground, right? A voltage when it's gone is ground. A current when it's gone is an open.
What happened to IG being 0?
IG?
Yeah.
What's IG?
Current
This current?
gate.
This?
Yeah, the other current isn't zero, right?
What happened to it? Nothing. It's still 0.
It's gonna float it in.
There's nothing gonna happen to it. It's still a 0. I'm saying that if you connect that to ground, so now you have 2 grounds here, right? And these 2 are in parallel, but that doesn't matter. This current IG, like you said, is 0, right? So there's no current passing through these 2 resistors. So the voltage over there is still 0.
There's nothing.
It's still what?
0. It's an Ohm law. When there's no current passing through resistors, the voltage across them are going to be the same, right?
I get that.
So it's a 0. So the voltage in the gate is 0 when V sig is 0.
Okay, yeah, sure.
So gate is ground, and looking from the source, you see 1 over GM, and the drain is ground, so you see 1 over GM.